But let's see, if you are doing a force diagram, let's say I have a force here, and I have a force here, and I have a force here of thing. And let me set a scale. So the force scale is 1 Newton per millimeters. So I can go back and say that Newton per millimeter. This is because I don't have the Newton millimeter unit set in my unit system, so I can come back and look at the display unit, but I could have also set up the units in my unit system. So coming back, so this let's say this force here is 20 newtons. Let me just attach it to the end of this line, the cell, so it will stay with it. So what I'll do is I will say we need to know what is the length of this vector. So click here, and it is really this value divided by my scale. This is my scale. And let's say the force is here, I'm going to put it at the end of this line, is 30 newtons. And the force on this one is, I'm going to attach it to this thing, and let's say is 14 newtons. I can flip the cell, so just go here and go right. Okay. So I need to know what would be the resultant force. So what I do is I create parallelograms. I say, okay, I just draw a line from here to here. It just snapped on the vertical from the end of this to this direction. Then what I do is I free up this line, because when it snapped to vertical, it had an angle allocated. So I can say this line is parallel to this line. Sorry, this line is perpendicular to this, is parallel to this line here. Okay, and constrain the end to the end here. And then what I'll do is I'll trim this line by double clicking on this point and say it's on this line. And likewise, I'll double click on this and say it's on this line here. And then I will constrain a line from this point to this point. So that's the resultant force of these two forces. Now I have to find the resultant force of this and this force, so I do the same process, and here just draw a line someplace, and here draw a line someplace. This is parallel to this, and this one is parallel to this, and then it's coming on, it's being trimmed by this, and this is trimmed by, and then I draw a vector here from here. So this is my resulting force. You can put a color on this so that it's easier. So I have a basic force vector diagram, and now if I change the orientation of the forces, I can also put arrows on the various forces. So this was the second force. I want the arrow on the other side, and here likewise put the arrow. So these three are variable forces. So you see how the parallel thing helped us in moving things around, in getting a force diagram. But this was when we were making parallelograms. But let's take a situation that let's say a spring is attached here. So this will exert a force because when the spring is stretched, it'll pull this arm back. So what we do is we make this perpendicular to this. And if this is the force vector of the spring, then what we can do is make a line which is perpendicular to this and then trim using this line and trim using this line. So and you can do a scale, but to give you an idea, this is the length here and this is the length here. So if this, I'm going to fix it here. If this thing moves, you'll see how the force is changing. This force vector, the value changes. So this will be a very interesting and easy way to do force propagation. You can just keep creating this force vector diagrams using the parallel and the perpendicular preset constraints. And the last preset constraint is called the angle to constraint, and essentially what it is that if I have a geometry and I create another geometry, I can say make this angle to, you enter a theta value, let's say 45 degrees. The t value is 45, and you do not press the enter key again, just type in the value and select the target. So now when this moves, so this is interesting to build levers and stuff like that, and also useful for creating rigid bodies. So let's say I create a basic shape here, and then I say that this is at theta is 90 degrees with respect to this line. Actually, it's not 190 degrees, it's 270 degrees. Let's try 90 degrees and see what happens. You'll see the line flipped. So let's go and do theta of 270 degrees. T270 with respect to this. And now if this line changes, you see this is behaving like a rigid body. So when you want to create a rigid body, I can give it a length constraint, let's say 40 millimeters, and now it'll stay as a rigid body. So when you create a rigid body, you can use the angle to constraint and then constrain each element of the boundary with respect to the previous entity, and then you can define a rigid boundary this way. And I'm gonna delete the area. Let's punch a hole here. This is where you will see the power of the software, the circularity. So I'm going to put a radius 5 millimeter hole in there, and then define the area and say this is at the centroid of the shape. Now if I animate this thing, you see the circularity will be maintained. So this is a technique. So the parallel, perpendicular, and angle to constraints come in handy when you want to have a specific relationship between lines. Thank you.